Hey everybody, welcome to our video on dienes. Good morning or good evening wherever you are. I'm here at midnight at North Bend Rainbow Lodge, which is this beautiful little retreat center where I'm having a teaching and learning conference with a bunch of colleagues from all over the United States, and it's great, but man, it's a lot of work. But we are located right near Mount Si, so I could see Mount Si from just outside the window. But anyway, we are almost done with Chem 262 now. We just have dienes, and then we have conjugated systems, and then we have electrophilic aromatic substitution reactions of benzene. So we're almost there. We want to start with this idea of diene, which is a molecule with two pi bonds. So think of it as two alkenes, diene. So di2-ene alkene. So there's different ways that these double bonds can be arranged. They could be right next to each other, which we call cumulated. So you could see this is 180 degrees. So this carbon, do you know the hybridization that this carbon would be? That would be sp, right? If we have sp2 carbons, then you could have either conjugated, which means you have alternating pi bond, sigma bond, pi bond, sigma bond, pi bond, and you could have many long chains, just like beta carotene, the stuff that makes carrots orange. That molecule is conjugated, which means a lot of conjugated molecules have this property of absorbing visible light, so they end up being colored compounds. And then isolated double bonds are ones that are not conjugated or in that alternating pattern. So in this molecule here, we would think of these two pi systems as being separate, and we would think of conjugated system as having a different property, which I think you guys would see. We have resonance, so that means this pi system is actually spread out through delocalization over this entire region, and so they're going to behave differently. Other conjugated systems could also be with a carbonyl group instead of two alkenes. We could have an alkene with a carbonyl group called an enone. Do you guys know where that name enone comes from? So ene means double bond, so that's this, and one is referring to a ketone or carbonyl, which it could also be an aldehyde technically. Enal would be with an aldehyde, enone with a ketone. But in any case, the important part is that there's conjugation there. And when you have conjugation, you have resonance delocalization. And for those of you who have done the Carvone epoxidation lab, you know that part of Carvone has resonance stabilization with an enone functional group, something like this, where you can have resonance across this whole system. So that's going to be a very important theme, especially in Chem 263. Next quarter, there's going to be a whole section on the chemistry of enones. So keep that in mind for later. So for this exercise here, we want to look at using the terms cumulated versus conjugated versus isolated. So back to this idea here, and just identifying what kind of system you have so that you can use that as a basis for understanding properties and reactivity later on. So let's just do one as an example. Okay, so I'm looking for conjugation is pretty easy to identify because you'll usually see alternating pi, sigma, pi. So see this pi here? Sigma, pi, sigma, pi. This whole system here is conjugated. But see here it's sigma. I would need a pi right here, and I don't have that. So this is isolated right here. So this pi system here is isolated. It's not a CC double bond pi system, so you don't have to label that one. But this CC double bond system is conjugated with these two carbonyl groups. For this one here, go ahead and label which double bonds are conjugated and which ones aren't. All right, so hopefully you guys see that that's a conjugated system right there. You see the alternating pi, sigma, pi. So this is conjugated, and this part is isolated. All right, because conjugation results in a more stabilized, delocalized pi system, those are favorable in terms of being formed. So see right here, we're used to tert-butoxide is a strong base. It can take any of these beta hydrogens. So it can take either those beta hydrogens or those beta hydrogens. Remember, beta is referring to the leaving group is on an alpha carbon, and the next door one is the beta hydrogens. So of all of these, you could imagine the first possibility is it could take this, and then that would make a cumulated pi system like that. Or it could take one of these other ones, and we can make the conjugated system right here. So whichever pathway is favored is going to be the one that usually makes the more stable product because of the Hammond postulate, right? So we would say that the conjugated one is more favored because of that resonance delocalization. And we see the same thing here as well. You have options of different beta hydrogens, but it's more favorable, lower activation energy to make the more stable diene that's conjugated. So if you guys remember, the shorter the bond length, the more stable and the stronger the bond is. So if we look at a regular alkane carbon-carbon bond, we see the bond length is about 153 picometers. Pico meaning 10 to the minus 12 meters. Okay, so very small. When we look at this middle sigma bond here, so these are both sigma bonds, we see that it's actually quite shorter, so 148 rather than 153. Not too much shorter, but a little bit shorter. And so that can be explained by resonance delocalization. Double bonds are shorter than single bonds, and triple bonds are shorter than double bonds. So that's telling me that this sigma bond actually has some pi character because it's shorter. And that pi character comes from this kind of delocalization here due to resonance. It can also be explained by hybridization. We know that the greater S character, the closer the electrons are to the nucleus. So the electrons, the valence electrons in these bonds can be held closer to the nucleus, bringing nuclei together, thus making the bond length shorter, as opposed to sp3, lower percent S character, more P character. So they're going to be farther out, hence longer bond length. Heats of hydrogenation also confirm that conjugated dienes have stronger bonds. If you react an isolated alkene with hydrogen and you hydrogenate the molecule to an alkane, you release this much energy here, negative 254. But if you take a conjugated diene and react it, it's less exothermic. So that difference in energy tells me this is more stable than this is because it gave off less energy. Okay guys, so let's try some practice problems. It's going to rely on some knowledge of reactions from before. So first, we want to make a diene, and notice that we had some reactions where we could do that up here. So we made some dienes from either two bromines, two leaving groups, or from a pi bond with one bromine to make a second pi bond through, these are both E2 elimination reactions with a strong bulky base. Or you could use also a small base as well. So in this problem, we need to first make a leaving group, but if we only do one leaving group, so remember, anytime you start with an alkane, you got to introduce some functionality, right? Can't do anything with this except this one reaction we learned, which is bromination. So you brominate it, and you get Br. But if we eliminate this, we'll only get one alkene, right? You'll only get this elimination right there. So what we need to do to get a diene is we need to, we could do a couple of things, okay? We could either put two bromines on here, and so I think you know how to do that, and then you can eliminate with NaOH. So this is one way you could go, and so just to fill in the reagents, we go from an alkene to a haloalkane by doing Br2, radical bromination with light, photons, or heat. Then bromine can turn into a double bond with strong base like NaOH and heat. That's E2 elimination. And then, I could use a bulky base or a small base in this case. once you get the alkene, you need 2 leaving groups because you need 2 pi bonds. So we're just going to use Br2 in an aprotic solvent like methylene chloride or ether. You don't have to specify. Then we've got 2 bromines. We need double elimination. Now, because this is a 6-membered ring, we're not likely to make a triple bond here because too much ring strain. Remember, a triple bond is 180 linear. So in order to make a ring out of it, it would be really, really highly strained. So here I can just use NaOH, or I could use KOTBU, as in the previous examples, because maybe the steric bulk will allow me to take these beta hydrogens over here, and then I'll make these 2 pi bonds here. Now maybe a few of you can think of another way as well. So one other way is you could take this, and since it already has a pi bond, you can do a allylic bromination. Okay, remember that's the allylic position, either here or here next to the double bond. And remember that's with NBS, or heat or light, right? Remember that's NBS, with heat or with light. And so we have allylic bromination, and then we can have elimination of this using KOTBU and heat. All right, but the main big idea here is making a molecule with conjugated diene. In the next problem, we want to rank the CC bonds in terms of bond length from shortest to longest. So first, we'd need to draw 1 butene. So let's do that down here. 1 butene right here is 1, 2, 3, 4, like that. And they want to know, here's 1 CC bond, here's the other, and here's the other. There are 3 CC bonds. So, of course, we would think that the double bond will be the shortest because it's the strongest. And then this will be the second shortest because it's an sp2 and an sp3. And then these two carbons here are sp3, so they'll be the longest. And then finally this last problem, of course these 3 drawings go with this last problem. Compare the following 3 isomeric dienes. They're all dienes and they all have the same number of carbons and hydrogens, so they're isomers. A, which compound will liberate the least heat upon hydrogenation? So thinking back to the more unstable you are, the higher your heat of hydrogenation, the higher your potential energy. So when you fall down to a more stable compound, you're going to release more energy because you're way up here. If you're more stable, you're starting in a lower energy position, so you're going to release less energy. So make sure you understand the more unstable stuff is higher energy, the more stable, the lower energy. And this reaction is hydrogenation, meaning you are adding hydrogen to make an alkane. So how much do they fall down to make that alkane in energy? How much do they fall in energy? So when they ask for least heat upon hydrogenation, they mean a smaller delta H. So they mean the more stable one. So the more stable one will be, can you guess which one it is? The key is the conjugation. So this one will be thermodynamically more stable. So this one will be the answer to part A. For part B, which compound will liberate the most heat upon hydrogenation? So for that one, we're talking about the least stable diene. Now this one might be trickier because these are both isolated, right? So if they're both isolated, how can we tell? Do you have any ideas about that? Well, if you think back to Chem 261, and we talked about Zaitsev versus Hoffman, and Zaitsev is the more stable alkene, right? So between these, we know that the more substitution there is, the more stable the alkene is. So let's take a look. These 2 double bonds are equal, so that's not going to tell me. Let's examine these 2 double bonds now. Of these, which double bond is more stable? Well, this one is mono-substituted, 1 R group, but this one is tri-substituted. So that tells me this one's going to be more stable. So the answer to part B is it's likely to be this alkene on the left. And this is most heat upon hydrogenation. And this one is the more heat upon hydrogenation, which is the least stable of the three. So the thing about dienes is that even though there's some double bond character here due to resonance, there's still the ability of rotation. So this can rotate here, and you can have two forms of a diene. You can have a conjugated diene that is S-cis, where S is short abbreviation for sigma. That is about the sigma bond, there's rotation, S-cis, so that the double bonds are on the same side, or after rotation, they could be on opposite side. And this bond here can rotate. So now there's this equilibrium that can exist between the S-cis or the S-trans form. And that equilibrium usually favors S-trans a little bit more. Can you guess why? Of course, these two groups prefer to be farther apart due to steric hindrance. Now we're going to take a little bit of a departure into something called molecular orbital theory. And you've probably heard of this before, talk about it a little bit in Gen Chem and beginning of Chem 261. So when you think about electron configurations and just an atom, and it's got orbitals, s orbital 1s, 2s, 2p, x, 2py, 2pz, and so forth. You can just build orbitals onto an atom. When atoms get together, they form molecular orbitals. Those atomic orbitals get together and they form molecular orbitals. So when you think of a molecule, it doesn't have atomic orbitals, it has molecular orbitals. And those orbitals get populated in an energy diagram, just like the way we would draw an energy diagram for a single atom. So here's an example of that. We have atomic orbitals like 2p for one atom. We have another atom with 2p orbital over here. So see, there's a carbon with a 2p orbital and another carbon with its 2p orbital. So some of the 2p orbitals, they get together and they form a sigma interaction. If they're side to side, they form a pi interaction. They can form different pi interactions. So we could have pi bonding or pi antibonding, or we could have pi non-bonding. So there's all different kinds of energy values these could have. Notice that when you have two electrons that pair and go into a lower energy molecular orbital compared to the atomic orbitals, you get something called a bonding molecular orbital. And this means that the phases add up together. So let's say that you have a 2p orbital like this. You've got a bottom lobe and a top lobe. And let's say this p orbital is also bottom lobe and a top lobe. And when these two get together in phase, notice that the reds add up together and the blue parts add up together. So that means it's in phase. That contributes to a good bonding interaction between those two orbitals. If, for example, you have one of these reversed, so let's say this one over here on the left has now flipped. So it's possible that this orbital may be blue on top and red on bottom. And it's not that these orbitals are actually blue or red. It's just that there's sometimes people use positive and negative, or sometimes they shade it in and one's not shaded in. In any case, they're two different characters to this orbital. And so if you have a blue part interacting with the red part, they are now out of phase, whereas they were in phase before. And when you have out of phase orbitals, then that creates a node. And so that node is thought of as a place where there is no electron density. See how there's no electron cloud in that region? All right, so it's good to know that a node is an area where you have less bonding capability, less interaction between those lobes. So that contributes to what we call anti-bonding molecular orbitals. And they are basically where bonding would be destabilized, as opposed to bonding orbitals where bonding is stabilized. So I want to show you how we can build a molecular orbital diagram from scratch. And the classic example is 1,3-butadiene. So let's try that. First, we would draw a structure, Lewis structure. 1,3-butadiene, so we've got but 1, 2, 3, 4. 1, 3 means double bond at 1 and 3. So here's 1,3-butadiene. Now, because there are 4 carbons here, I want to consider the 4 carbons as having these p orbitals. Why am I picking p orbitals? Because I'm mainly interested in studying the pi system. Now, the first level always has the orbitals in phase because that's the lowest energy. You have the greatest bonding interaction when you have that. Now, your energy diagram should always have an axis in the y for energy or potential energy. And then you've got your 4 orbitals here, 1 for each carbon. And this first level is called psi 1, Greek letter psi. So technically, the way we would visualize this molecular orbital down here is that these 4 would add up, and we'd get these blue ones in phase make the sort of molecular orbital. Looks like a sandwich or Oreo cookie. You have this one, and then you have the bottom like this. And this represents a molecular orbital, like this. And here are your 4 carbons, like that. Okay, but actually the double bonds are spread out. So now to draw the next set of molecular orbitals, it would be to try to envision one node. So here there is no node, but if I put in a node, there would be some symmetry. So let's say there would be 4 carbons, first of all, and I would have, for symmetry, one node needs to be through the middle. And so what that means is I'm going to have these guys be in phase, but wherever the node occurs, I'm going to switch the phase. So now my phase is going to be so that the red is up and my blue is down. So see how the phase has changed at this node. So what this looks like then is I've got some interaction here. These guys right here overlap, and these guys here overlap. But I've got this node right here. And so that sort of should remind you of something like that right there. And so this is called psi 2. This is our second level. So I challenge you guys to think of a way to put in 2 nodes now. Remember, you can only have these 4 carbons because we're talking about this molecule right here, 1,3-butadiene, so 4 carbons. And how do I put in 2 nodes in a way that is symmetric? So to put in 2 nodes, we would do this. So let's try our color scheme here. I'm going to have this one, and then I'm going to switch phases. Now this one is going to be same phase, and then I'm going to switch again every time I encounter a node. So now I fill in with the rest of the orbital. So this is my psi 3, higher energy because I have 2 nodes now. I have more out of phase than before. And you can imagine what that molecular orbital looks like. I've got something like this. I've got a node, then I've got this interaction right here. It's overlapping between carbons 2 and 3, and carbons 2 and 3 in the middle. Then I've got this other node right here. Right here is right here, okay? And then I have this one left, so I'll draw it on the end here. So that's sort of what level 3 looks like here. Okay, so last one. Can you guys draw the 4 carbons and tell me, where are the nodes? How many nodes do we need at this point? Well, we had no nodes for lowest energy, 1 node, 2 nodes. Now we need 3 nodes, and they would go right here. So that means I'm going to have to switch phases at every carbon. So you guys may notice something here. In terms of stabilization, we like to have really good overlap and electron densities that are additive or constructive interference, where the waves add up together because they're in phase. Okay, so you can see this is the best situation for that. This means that the bonding interactions are good. So that's why it's lowest in energy. And you can see how as we increase in nodes, that bonding becomes more choppy, right? It's not very coherent up here. So that's why it's so high energy up here. The terms that we use are bonding versus anti-bonding, and that has to do with symmetry as well. Instead of the nodes which are symmetrical vertically, we talk about putting all the energy levels and then splitting it up. So that is, the middle here would be non-bonding orbitals, but we don't have anything in the middle. We have 2 below the middle and 2 above the middle. So there are no non-bonding molecular orbitals. We would say the lower half are going to be the bonding molecular orbitals. So these 2 are considered bonding MOs. And then we would say that the 2 upper ones are considered anti-bonding MOs. MO being molecular orbitals. And along with these, just like with atomic orbitals, you have a slot for electrons. So let's do that. This is the pi system. Remember, we're only considering the p orbitals, not the s orbitals. And we're considering the 2p specifically because carbon's valence shell is 2p. And what we're doing is we're occupying these molecular orbitals with electrons in the pi system. So we want to count how many pi electrons there are in this molecule. So here's 1 pi bond, 2 electrons, plus 2 electrons. That's 4 pi electrons. So the last step of the molecular orbital is to fill it with electrons. So for every orbital, we can fill it with 2 electrons. So I want to have a slot for each of these orbitals. And I didn't make a lot of room, but I'll just stick them right here. So if I have 4 pi electrons from this bond and this bond, I'm counting only the pi bonds, then I'm going to have 1, 2, 3, 4. So because I'm occupying the most stable molecular orbitals, the bonding molecular orbitals, that tells me that these pictures are the most accurate for this molecule, that there's a lot of strong bonding interactions, and that helps to explain the stability of this molecule. It also explains, if you look at side 2, the reason why is because of symmetry, that these 2 have good bonding interaction. Obviously, that's where the pi bond is. And between carbons 3 and 4, there's also strong bonding interactions there. And slightly less through this middle bond here, because that's the sigma bond. But because of resonance, that part is explained by psi 1, the fact that they are all in phase in their lowest energy bonding molecular orbital, and that accounts for the resonance that we see across the entire system. And so that's what is explained in this next picture. The lowest molecular orbital, energy molecular orbital, shows the pi character that's spread across the entire system, which is how we think of resonance, and then also the idea that the double bonds are mostly between carbons 1 and 2 and between carbon 3 and 4. So there's some disconnect between carbon 2 and 3. The last thing I want you to do with your MO diagram is to label the highest occupied molecular orbital, and we call that the HOMO. So the highest occupied is you look at which ones are filled and you look at the highest energy of the ones that are filled. So this one right here. So this molecular orbital is called the highest occupied molecular orbital. And then we also want to label the lowest unoccupied molecular orbital, or the LUMO. So you look at the next one that's empty, that's the lowest energy of the ones that are not filled yet, or unoccupied. So this is the lowest unoccupied molecular orbital. Why are we interested in these? There's this whole idea called frontier molecular orbital theory, frontier molecular orbitals. So when do you guys ever hear the word frontier anyway? It's sort of in the context of the Wild West, right? Well, so the reason we care about frontier molecular orbitals is because they are the ones that are usually involved in chemical reactions. And we'll see an application of this later on in the chapter.